Hello students, welcome to Software Classes. This is Dr. Sarkar over here. Now we are going to today discuss the synthesis of aldehydes and ketones, which will be our first part of the lecture. Before going to the strategies by which we are going to retrosynthesize these aldehydes and ketones and find out what are the starting materials. So let's first understand what is the synthesis procedure. So we will say that aldehyde and ketone both carbonyls can be created via FGI and also from compounds already containing the carbonyl group can be functionalized by reaction either the at the electrophilic center, which is obviously, say suppose this is the carbonyl group joined to some X, so this is my plus, so this is my electrophilic center. Okay, for example, the acyl substitution reaction or at the nucleophilic alpha carbon. And when I say this, I mean if this is your carbonyl, then this is your alpha carbon. So let us consider in the first part synthesis of aldehyde ketones via functional group interconversion. So basically out here we are going to consider these procedures, which include oxidation of alcohol, in the second we will consider oxidation of alkenes. Alright, our third will be partial reduction of carboxylic acid derivatives. Alright, and in the fourth we will say hydration of alkynes. So what are the reagents for such a thing? So suppose we are thinking of oxidation of primary alcohol, then out here we are saying reagents, and this is going to give us our aldehyde. So just we will list these reagents. So in one we will say pyridinium chlorochromate, which we call PCC, and the solvent out here mostly are, say, dichloromethane types, can also be chloroform, or we will say pyridinium dichromate, also known as PDC, solvent being the same. We can use Swern oxidation process, which is basically DMSO in presence of COCl2. Okay, we can also use open-or oxidation process, which is basically aluminium trialkoxide in presence of so for this one we will use benzoquinone. Okay, so these are the reagents commonly used, okay, for such oxidation. And if we were to consider oxidation of a second degree alcohol, then we will consider, say again, reagents, and we will say out here we are going to use PCC, PDC, Swern oxidation. We may also use Jones reagent. Jones reagent is not used in the case of primary alcohol because it will further oxidize the aldehyde produced to the acid. So Jones reagent is basically Na2Cr2O7 in presence of concentrated H2SO4, solvent being the acetone. We may also use the open-or oxidation process, and here we will use aluminium trialkoxide in the presence of, say, acetone. Alright, rather better to mention isopropoxide. Okay, so these are the list of reagents that can help us to oxidize the alcohols to our desired aldehydes and ketones. Okay, now for esters, so for the acid chloride or for the ester or for the amide, the reagent that one may use to selectively or partially reduce them to the aldehydes is a diol H in presence of THF at minus 78 degrees centigrade, and which has to be followed up with the acidic workup, and our desired product will be only and only aldehyde in these cases. Diol is also known as Dye Isoamyle Aluminium Hydride. Okay. Now, if we were to synthesize the aldehydes and ketones from alkenes, then what one may think of is the use of ozonolysis. So, suppose this is our structure for the alkene. So, whether a ketone or a aldehyde will be produced will depend on the structure of the alkene, that is, what the alkene bearing carbons are having. So, if we use ozone, and as a reducing agent we can use either zinc in presence of acetic acid or in water, or one may use dimethyl sulfide, or one may use triphenyl phosphine. So one can consider that the bond will be cleaved out here like this, and over here it will lead to the generation of the left hand carbon will be giving you the ketone, and the right hand part will be giving you the aldehyde. So it does depend on the structure of the alkene what our products will be, whether a ketone or aldehyde. In the next part we will consider the hydration of an alkyne. So suppose we have been given an unsymmetrical alkyne like this. Now if we are considering the usage of HgSO4 in presence of acidified water, then out here the addition is Markovnikov type. So here we are considering the addition of water to the alkyne group. So if it is Markovnikov type, that means in this case OH adds here and H will be adding here when we are considering this reagent. So what is the enol intermediate that will be produced? The structure will be something of this kind. Okay. This is our intermediate, which will be spontaneously tautomerizing to the ketone having a ketomethyl group, and a ketomethyl group will always be obtained whenever we are having a alkyne which is having a, or it will be obtained from a terminal alkyne. Okay, so this is a terminal alkyne. So whenever we have a terminal alkyne, there will be a ketomethyl group. So this thing should be kept in mind by the students. Now, so whenever you see a ketomethyl group, you can think backwards there will be a terminal alkyne. However, if you are using the hydroboration oxidation process, which obviously involves Dye Isoamyle hydroborane followed by, so this is the reducing agent followed by H2O2 in NaOH, which is the oxidation process. Our enol out here will be of this structure and which will be tautomerizing to the corresponding aldehyde out here as shown. So this is going to give us a aldehyde, that is the hydroboration and oxidation process, whereas the mercuration process will give us the ketone product. So here, while considering the production of the enol, one has to think of anti-Markovnikov addition of water to alkyne, whereas this is Markovnikov addition of water to alkyne. So these are the two basic differences while we are considering such reactions. Okay. So I think we have discussed most of the part relating to this topic we wanted to. Now, why use a Dye Isoamyle Borane out here? Dye Isoamyle Borane, I would like to stress, sorry, it is Diisoamyle Borane. Now here it is basically a bulkier borane reagent, which can be seen from the structure which I will write below, and provides anti-Markovnikov selectivity. That is why we are using this reagent and not simply the BH3 in THF. So this is the structure of the reagent that we are using out here. Okay, thank you for listening. This is Dr. Sarkar saying goodbye. Keep visiting Sarasa classes for further lectures on retrosynthesis. Thanks. Have a great day.